Hi guys. In this lecture series of complex analysis, up to the last lecture, I discussed analytic function. And just in the last lecture, I started another function, that is the harmonic function, in which I told you first thing, what is harmonic function, and also I told you what is the relation of harmonic function and analytic function. So I told you if we have function of two variables, then this is harmonic if it satisfies is this second order partial differential equation, means del square phi by del x square plus del square phi by del y square equal to 0. Then we say that phi is harmonic function. As you know that, and I told you, this is a Laplace equation. This is a second order partial differential equation. If phi satisfies this, then this is harmonic function. And after that, I expressed a property related to the analytic function, in which I told you if fz equal to u plus iv is analytic function, then I told you u and v both are harmonic. Both are harmonic. Means if function is analytic, then its real and imaginary part, as I told you, here we are taking complex function fz is equal to u plus iv, where you know that u is a real part and is a function of xy, v is also imaginary part, also function of xy. So both are here harmonic, means both u and v satisfy Laplace equation. And here v is said to be conjugate harmonic to u. Right? First I told you this, and then I took up some numerical examples, sums, in which we see that how you can check any given function whether it is harmonic or not in last lecture. And also on last lecture I just introduced one thing, that is I introduced construction of analytic function. I just introduced in last lecture, and this is the last topic of this chapter, construction of analytic function, in which I told you one method, that is Miline-Thompson method. We used this method, Miline-Thompson method, in which I told you if fz equal to u plus iv is an analytic function, then there may be four cases. First and second case I discussed on last lecture. First case, if real part is given and fz is to be found. First case I discussed this, in which by Miline-Thompson method I defined a formula fz equal to integral phi of z comma 0 minus I phi 2 of z comma 0 dz plus c. That was the formula for analytic function. Here we use as phi 1 of xy function, means it is partial derivative of u with respect to x. Phi 2 of xy is partial derivative of u with respect to y, because u is given. So first you have to find partial derivative with respect to x. It is expressed as phi 1 of xy, and partial derivative of u by v is taken as phi 2 of xy, and from these two you will get phi 1 of z0 and phi 2 of z0 by putting x equal to z and y equal to 0. Now substitute these values here and integrate with respect to z on the right hand side, you will get your required analytic function. Second case I discussed when imaginary part is given and fz to be found, in which I discussed by Miline-Thompson method fz is defined as function psi 1 of z0 plus I times psi 2 of z0 dz plus c. This is the second case, when imaginary part of the given function and you have to find the analytic function. Then we take this formula, and here psi1 and psi2, I told you here psi1 function of xy, this is partial derivative of v with respect to y. This is important thing. We first here taking partial derivative with respect to y, and second psi2 of xy is partial derivative of v with respect to x. And again, by these two functions, we can obtain psi1 z0 and psi2 z0 by putting x equal to z and y equal to 0, and substitute these values here, you will get required analytic function. That was the third case. Up to this case, I discussed in the last lecture, and just I am repeating here. And two cases also here. First, if you imaginary real part and imaginary part are not given, but in some numerical sum, you see that there will be given sum of real and imaginary part or difference of real and imaginary part. Suppose that is the fourth case, third case, when u minus v r is given, difference is given, and then you have to find the analytic function by Miline-Thompson method. And today I first discuss these two cases, even difference of real and imaginary part is given or sum of real and imaginary part is given, and you have to find the analytic function. If u and v is given, suppose we know that we have fz equal to u plus iv is analytic function, which we have to find. So multiplying I on both sides, we get iu minus v. Now adding this 1 plus I into f of z, real part is u minus v, and plus I times u plus v. Now take this capital Fz, say in the left hand, and this is capital U, this is capital V, right? This is as equation 1. Now we change the notations by taking u minus v as capital U, u plus v is capital V. Now here capital Fz is analytic function, capital U is imaginary real part, and capital V is imaginary part. Now we can use Miline-Thompson method. If u minus v is given, then first case may be used because real part is given. If imaginary part is given, then second case may be used. This is third and fourth case, means u minus v is given and u plus v is given, right? These are the four cases in which we can use Miline-Thompson method. Means first, I told you, if fz equal to u plus iv is an analytic function, real part u is given and you have to construct analytic function. Second case, when imaginary part v is given and you have to find the fz. Third case, if difference u minus v is given and you have to construct analytic function. And fourth case, u plus v is given and you have to construct analytic function. These are the four cases in which we can construct analytic function. Now, to further explain this, here I am taking numerical examples on each case. First, here I am taking example, the real part of analytic function is given and you have to construct analytic function. This is the first example. First example, determine fz u plus iv analytic function as real part u equal to x cube minus 3xy square plus 3x square minus 3y square plus 1. That is the real part of this analytic function. This is given and you have to find the fz. Now, first I take this example. Given that u equal to x cube minus 3xy square plus 3x square minus 3y square plus 1. Now, first find the partial derivative of u with respect to x, del u by del x. This is 3x square minus 3y square plus 6x. Right? Take it as phi 1 of xy, say. And so, from here, we can obtain by Miline-Thompson method phi 1 z0 by putting x equal to z and y equal to 0. Then we get 3z square plus 6z. We get this thing. Similarly, we find partial derivative of u with respect to y. That is, first term is 0, second is minus 6xy. This is 0 minus 6y. Take this as phi 2 of xy. Assume this. So, from here we can obtain phi 2 z0 by putting x equal to z and y equal to 0. So, this is 0. Right? Now, by Miline-Thompson method, we know that now by Miline-Thompson method, we know that analytic function fz is integral sign phi 1 of z0 minus I phi 2 of z0 dz plus c. Now here you substitute the value of phi 1 z0, you have already calculated, and phi 2 0. This is under integral sign. This is 3z square plus 6z, and this is I into 0 dz plus c. Simply calculate these values, and now right hand side integrate this with respect to this. This is z cube upon 3, 3 is cancelled out. This is z square by 2, 2 is cancelled out, z square. This is 0 plus c. This is your answer. This is your required analytic function, and this is Miline-Thompson method. And that was the first case. Even a real part is given, then how you can construct analytic function. I am repeating again. Here we have to construct analytic function as z when its real part u is given. Then what was the process? First, I take del u by del x and substitute this, assume this as a phi 1 of xy. From here we obtain phi 1 z0. Then we take partial derivative of u with respect to y, take this as phi 2 of xy, and by putting x equal to z and y equal to 0, we obtain here phi 2 of this. And now substitute these two values in given formula of Miline-Thompson method, we can obtain required analytic function. This was the first example of construction of analytic function when real part is given. Now, second example, that is example of the second case. You find the analytic function when imaginary part is given, in which we take this example, this numerical, show that e to power x, x cos y minus y sin y is a harmonic function, and also find the analytic function fz for which e to power x, x cos y minus y sin y is imaginary part. This is the numerical example depending on second case. You find a constant grandian function when imaginary part is given. See its solution. Given that imaginary part means v, e to power x, x cos y minus y sin y. This is the imaginary part is given. First, in the first part of the question here, we have to prove it is harmonic function. For harmonic function, we have to show that it will be satisfied Laplace equation. So first we get del v by del x, that is the partial derivative by multiplication rule, e to power x. This differentiation of first function into second function plus first function differentiation of second function only cos y, because this del v by del x means this is, if you take common out ex, that is x cos y minus sin y, y plus cos y, right? And you can take as phi 1 of xy. Now calculate del 2 by del x2, because you have to prove also it is harmonic function. Means second derivative of this with respect to x. Again multiplication rule, first function into second function plus first function, differentiation of second function with respect to x in this function, only this is the function, so we get again cos y. This is the second derivative. Similarly, calculate partial derivative of v with respect to y. Now first del v by del y, again ex, that is function of x, only we differentiate this function partially, x, differentiation of cos y minus sin y. This is multiplication rule, y is 1 and then y sin y is cos y. Simplify this, this is e to power x minus x sin y minus sin y minus y cos y. Take it as phi 2 of xy. Now differentiating it again partially with respect to y. Again by multiplication rule, first function, that is not function of y, so this is the first function. We have to differentiate only this function with respect to y. Then this is minus x, differentiation of sin y is cos y. Differentiation of sin y is cos y. This is by multiplication rule. First function y cos y minus y sin y. This is finally ex minus x cos y, that is 2 cos y. This is and minus plus y sin y. This is the second derivative. If you add these two, del v2 by del x2 and del v2 by del y2, then you will get 0. All terms are cancelled out. So here we can say that v is harmonic. That is the answer of first part of the question. The given function v is harmonic. Now here again v is given and v is the imaginary part of this function, and we have to construct analytic function. For that we again use Miline-Thompson method. So by Miline-Thompson method, we have fz equal to integral, and sorry, this is with respect to x, so this is take as not phi 1, but this is as psi 2 of xy, or this is with respect to y, so this will be taken as psi 1 of xy. Formula is psi 1 of z comma 0 plus I times psi 2 of z comma 0 fz plus c. Now substitute the values. Psi 1 z0 can be obtained from here by putting x equal to z and y equal to 0. So this is 0, this is 0, and this is 0. Means first term is completely 0 by putting y equal to 0. Psi 2 z0 from here you get e to power z plus I times y is 0 and x is 0. psi-2 form. So fz is, this is psi1 xy. So from here we get x is 0, y 0. So this is 0, and in this case we get this, so psi y 0, x is z. So this is 0, and e to power z in bracket, this is cos z, because x is z and y is 0. So this is cos 0 is 1, this is z, this is completely 0, and this is 1 because cos 0 is 1 and dz. Now simply integrate this, you will get required analytic function, and I is common out. We have integral of this function. So this is the first function, this is the first function, take it, integrate by parts, you know the formula, that is first function, integration of second function minus integration of such function, differentiation of second function, that is 1. See, again we get I, if we take z, e to z is common, z plus 1 minus 1 is cancelled out, we get only z plus c. This is the answer, this is the required analytic function, and that is the example of second case when you have to construct analytic function and imaginary part is the given. Now in this series I am taking third example that depends upon your third case, third or fourth case, in which I told you in other case if real and imaginary part are not given but their difference or their sum is given. So I am taking here their difference is given, that is the this third example, example third, if u minus v equal to x minus y in bracket x square plus 4xy plus y square. If u minus v and fz equal to u plus iv is an analytic function. This is an analytic function of z equal to x plus iy. Then find fz in terms of z. This is the sum, and this is the sum based on your third or fourth case of Miline-Thompson method. Okay, now here difference of real and imaginary part is given and you have to construct analytic function. In previous two sums, real part or imaginary part is given and you have to construct analytic function. But here real and imaginary part difference u minus v is given. First we calculate this thing here, given that fz equal to u plus iv. If we multiply it by I on both sides, we get I into z, I into u minus I square is minus 1 equal to z. This is, and if add this 1 plus I into fz, real part u minus v plus I times u plus v. We calculate, we transform this into this form. Take this as capital Fz, this as capital U, and this is capital 1, and take this one. By this equation now, we change the transformation. Here, our function is capital Fz, that is analytic function, and capital U is difference u minus v, which is given, and capital V is the sum of u plus v, right? So here, now question is slightly changed by this transformation. Now here, real part of the analytic function is given and you have to find the analytic function fz. So this was the first case of Miline-Thompson method. As I took the first example, here first, given that capital U means u minus v, this is equal to x minus y, x square plus 4xy plus y square. To calculate this thing, open the bracket, multiply this, that is x cube plus 4x square y and xy square minus xy square minus 4xy square minus y cube. If we multiply these, means we open these two brackets, we get this by x cube by 4x square y or plus xy square then minus y minus x square minus by minus y, that is x cube minus 4x square y plus xy square. This is minus x square y, this is minus 4xy square minus y cube. This is again calculate this x cube 4x square y and x square y means 3x square y. Xy square minus this, that is minus 3xy square. Finally, we get this after multiplication this. So real part is given. So by Miline-Thompson method, first we have to calculate del u by del x. That is 3x square, 3y, 3 that is 6xy and minus 3y square and y cube is 0. This and we take this as phi 1 of xy for Miline-Thompson method. Now calculate partial derivative of u with respect to y, capital U. That is s cube with respect to this is 0, this is 3x square, this is minus 6xy and this is y 3y square. This is del y and we take this as phi 2 of xy, right? Here difference is given, multiplying by I and adding these, we change the transform and take it as capital FZ. So difference is denoting here capital U and capital V, right? This is, we are assuming this, taking this. So here real part is given, we open this bracket, we get this, simply multiplying this, open this bracket s cube and then 4x square, then xy square minus y minus x square y, all terms are negative, converting this. Now first derivative del u by del x, that is 3x square 6xy minus 3y square. We take this phi 1 xy. Del u by del y is from here with respect to y, this is 0, this is 3x square, this is minus 6xy this, and then by Miline-Thompson method we have the formula capital FZ. Here we have capital FZ by Miline-Thompson method. This is phi 1 of z0 minus I phi 2 of z0 dz plus c. This is the formula when real part is given. So from here, phi 1 z0 from here, you put x equal to z and y equal to 0. So from first case, we get only 3z square because y is here, so it is 0, y is here, it is 0. Phi 2 z0 minus I times, so y is 0, so this term is 0, this is 0, or minus 3z square, dz plus c. So this is after integrating, that is z cube minus I times z cube plus c. This is the right hand side, this is means take z cube is common, then 1 plus I, 1 minus I into z cube plus c. This is equal to capital F0. But by equation 1, capital Z is 1 plus I into small fz by equation 1. We assume this capital Z. So from here we get our original function, that is fz equal to 1 minus I, 1 plus I z cube plus c of 1 plus I. Further we can calculate this after multiplying its conjugate, because you know that I square root minus 1 and this can be this, so we have the formula that is 1 minus I, 1 plus I into z cube, and we can take it as another constant c1 because 1 plus I is also constant, so c upon 1 plus I is a constant, although it is a complex constant, so we get the required function, right? This is the third case. When real and imaginary part are not given, then this. By similar process, you can solve the sum in which sum of real and imaginary part is given. Again, because that is the second case of this imaginary part is given. So by these you can practice this and you can find the constitution of analytic function. After that, now I finish this topic completely, analytic function. And now in the next lecture, in this series complex analysis 1, here that is the first module, I will start complex integration. What is the complex integration? How you solve the complex integration? Because in complex analysis, in our introduction lecture, I told you, and in this topic, in this heading, complex analysis, we have to study about the calculus characteristic of a complex function. So first we study limit, continuity, differentiability, then analyticity, and now we reach up to the complex integration. Okay, thank you.